Hey everybody, welcome to week 9 of PS 398. Hope you're all doing great. We are now past the halfway point, if you can believe it. And you're like, oh no, I can believe it. I'm sure that you're really starting to feel some of the fatigue kicking in. I know I am. Just make sure that you're being good to yourself as much as you can. It's really easy just to focus too much on your work and cranking out stuff. And I'm not telling you not to do your best, but part of doing your best is being good to yourself. So I hope that you're getting enough rest. I hope that you're eating well. If I can be of any use in terms of directing you to my favorite ASMR stuff or more stupid recipes for college kids, just let me know. But chances are excellent that you know much more about both of those things than I do. You know, we find ourselves in the core of the class. We are talking about Nash equilibrium, mutual best response, steady state, all of the real nitty-gritty, holy crap, this is an IR game theory class sort of things. And so this is going to be the second part of our Nash equilibrium week. And what's interesting about it is we're going to see that there's actually a lot more to Nash equilibrium than you realize. So in the previous lecture, we talked about Nash equilibrium two ways substantively, right? So we talked about it as a steady state. It's a state of affairs in the sense that it is a choice made by every player, where nobody would unilaterally deviate. Conditional on what everybody else did, nobody would want to change their mind to some other strategy. They wouldn't have a strictly profitable deviation. And so the steady state is the primary way to think about defining Nash equilibrium. We also saw Nash equilibrium as the intersection of best response correspondences, and that's just a handy way for us to draw stars underneath numbers a lot of the time and get equilibria pretty fast. And it turns out that Nash equilibrium has even more going on underneath the hood. There's a third way to think about Nash equilibrium in terms of optimized strategic randomness, optimized strategic randomization, which is actually the core all the way, what is a Nash equilibrium sort of thing. And so we'll have to enrich our theory of Nash equilibrium to account for the potential for strategic randomization. It turns out that strategic randomization plays a really important part in many international processes. It's especially useful in games of anti-coordination like Matching Pennies, where one player wants one thing to happen and another player wants something else to happen. And not in a sort of Bach or Stravinsky, oh, we generally agree on that we would like to watch music together because we're musical companions, but we have differing preferences over the bargained outcomes. In Matching Pennies, it's much more like I win, you lose, ha-ha. Apparently that's how Matching Pennies goes, is I win, you lose, ha-ha. Let's try that together. I win, you lose, ha-ha. I win, you lose, ha-ha. I win, you lose, ha-ha. Oh, no spinning birds required. And if it was a game that ends in ha-ha and you lost, you can't really help but feel some regret about how things went down, right? I mean, it's not like, oh, well, I'm watching Stravinsky and I don't love Stravinsky, but I'm so happy to be with my musical companion, so I'll take it. I wouldn't rather change my mind and go listen to Bach by myself. Here it's going to be I win, you lose, ha-ha, and therefore you wish that you could change your mind, right? And so it's going to be really hard for us to come by pure strategy Nash equilibrium. We're going to have to think about a richer way to think about best response. And so that's what we're going to be talking about today. Mixed strategy Nash equilibrium, or just Nash equilibrium, it's the default setting. Mixed strategy Nash equilibrium is the way that we're going to think about this potential for strategic randomization in situations particularly where two players are engaged in behavior that's so nasty that they end in ha-ha. Along the way, we're going to learn some interesting lessons. The main goal for today's class is just to give you the technical capability that it takes to compute a mixed strategy Nash equilibrium in a relatively simple game, but we'll also see that strategic randomization is really important. And I want to show you that importance from two angles. I want to show you that strategic randomization at the international relations level has this interesting normative tension baked into it. You'll see what I mean. And then we'll also see that the tactics of the battlefield require really sharp focus on randomization, to the point that, oh my goodness gracious, World War II might make a little bit more sense to you after today's lecture is done. No promises, go watch Saving Private Ryan instead. That's way better use of your time. I suspect that we're going to have a lot to talk about today, so I'm not going to do any bloviating right now. Let's get to it. In the A block, I'll show you Nash equilibrium and Matching Pennies. I'll show you the insufficiency of a pure strategy approach, and I will show you how we enrich that approach to allow for mixed strategies, probabilistic strategies, randomized strategies. If I don't want you to know where I am for sure, then I've got to keep you guessing, and the way that I keep you guessing is by not doing the same thing every time, and the same for you. And so we're going to see that randomization, this natural logic of randomization, this natural logic of keeping somebody guessing, something that you've been doing ever since you started to play cards, something that you've done ever since you started to play video games, whatever games you play with somebody, whatever contests you play for fun as a hobby with somebody, you've been randomizing some of the time, I'm pretty sure. And so I want to show you how to encode that so that you understand yourself better. And more importantly, if you ever find yourself in a deep, dark game of matching pennies in some seedy basement somewhere, you're like sitting there with pennies and you don't quite know how to play it. I'm going to show you how to play it. You're going to be a cent richer in some weird basement. You're going to be so much richer because of me. You're welcome. In the B block, I'll show you that mixed strategy Nash equilibria can emerge in models with pure strategy Nash equilibria as well. We'll do so by looking at chicken. I love chicken, as you know by now. I promise I'll do my best not to sing any songs. I promised that I would do my best. I didn't promise I wouldn't sing. All I promised was that I would do my best. It's early yet, and this is black tea. There's a lot of caffeine in here. I can start to feel it coursing through my veins. I can feel the delightful sense of the Vitruvi aromatherapy device, just sending a delightful gargle of scent my way. There's no promises I'm not gonna sing. You might just want to put it on 2 times for that. 2 times the speed, don't repeat it. You won't have ears left. You'll be like Odysseus. We'll see in the mixed strategy analysis of chicken that there's a really stark characterization about the differences between waste and fairness. In the C block, I'll show you about the tactics of the battlefield by taking you to France. And we'll play a delightful game called Wait, Which Beach? You'll see what I mean when we get there. It promises to be a lot of fun. So lots to take in today. We're only going to study 3 games, but we're going to study them relatively thoroughly. And our notion of equilibrium is expanding too. So there's more going on underneath the hood in the games and in our equilibrium concept. We'll be expanding in 2 directions. There's a lot of different advantages to show you of these same mountains. You see them 10 different times, you see them 10 different ways, and they look like 10 different mountains, right? It's amazing. I hope that you're starting to see the beauty underneath these things, not just their prima facie coolness, but also their inner deep beauty. And in that sense, a game is kind of like your professor. So I'm really looking forward to showing this stuff to you, and it looks like I'm going to be sufficiently caffeinated to do so if all goes well. Fingers crossed. Hopefully some of this makes some amount of sense to you, but one never knows when there's this much caffeine in your professor's hands. Regardless, we gotta do what we gotta do. Let's get started. So here in the A block, I just want to introduce the notion of mixed strategy Nash equilibrium. What I've shown you up to this point, pure strategy Nash equilibrium, is only one kind of Nash equilibrium. It turns out that we'll also be allowing for something called a mixed strategy Nash equilibrium, and you'll see that pure strategy Nash equilibria are special cases of mixed strategy Nash equilibria. So what you've been shown up to this point is part of a more complete picture that you'll have all of today. The standard way to introduce mixed strategy Nash equilibrium is by motivating it through the anti-coordination game called Matching Pennies. So you'll remember from the games lecture that the idea of matching pennies is that I'm secretly flipping a penny, or the obverse and reverse of a $5 bill. I'm secretly flipping a penny and you're secretly flipping a penny. And then at the same time we reveal our pennies. And if they're both heads, I win both pennies. If they're both tails, I win both pennies. And if they're mismatched, then you win both pennies. So I want to see the same side of the coin up, and you want to see different sides of the coin up. Remember, that means that I can have heads up or tails up, and you can have heads up or tails up. And in the case where heads, heads, or tails, tails, that's 1 for me and -1 for you. And in the case of tails, heads, and heads, tails, that's -1 for me and 1 for you, right? So I want us to be on this diagonal, you want us to be on this diagonal. We have completely opposed preferences. There are no gains from trade, there is no opportunity for win-win. This is a zero-sum game. Notice that for all 4 outcomes, the utility numbers sum to 0, right? That's zero-sum. In general, if they sum to some constant, that means that I can't make one person happier without making somebody else sadder. That sounds awfully familiar. So, let's try to find all the pure strategy Nash equilibria of this game, and we'll start with heads heads. So at heads heads, I'm getting a happiness point and you're losing a happiness point. You just lost a penny. Holding you fixed, I wouldn't want to deviate because from heads heads, if I deviated, that would take us to tails heads. I would do strictly worse. I would lose because that would mean that we don't have the same side of the coin up. So I don't want to deviate, right? So I'm perfectly happy as we sit. But you want to deviate. Right now, you're getting -1 happiness points. If you deviated, if you knew that I was having heads up, you'd want to put tails up and get that happiness point that you get for a mismatch. So you would want to deviate, and because of that, heads is not a pure strategy Nash equilibrium. So that takes us to heads tails. So at heads tails, I lost, you won. It's -1 happiness points for me, 1 happiness point for you. You don't want to deviate for the reasons that we just discussed. From heads tails, if you deviated, that would take us to heads and you would lose, and so you don't want to deviate. However, I do want to deviate because right now we're at heads tails. If I played tails, that would take us to tails. I would win, you would lose. That's a strictly profitable deviation for me. Consequently, heads tails is not a pure strategy Nash equilibrium. So that takes us to tails, right? So we're at tails, which means that I'm getting a happiness point and you're getting -1 happiness points because you don't want them to be the same side of the coin up. You want mismatch, I want match. Think about it. For the reasons we just discussed, I don't want to deviate because if I deviated from tails to heads, that would take us from tails to heads tails. I would go from winning to losing. That's no bueno. I don't want to deviate. I'm happy as we sit there. But you do want to deviate because right now, at tails, you're getting -1 happiness points. And from tails, holding me fixed, if you deviated by playing heads, we'd be at tails, heads. And at tails, heads, you win and I lose. That's a strictly profitable deviation for you. Consequently, tails is not a pure strategy Nash equilibrium because holding me fixed, you want to deviate. That takes us to tails, heads. So at tails, heads, you're winning, I'm losing, -1. For the reasons we just discussed, you don't want to deviate because that would take us to tails and you would go from winning to losing. However, I do want to deviate. And the reason that I want to deviate is that we're at tails, heads. If I deviated to heads, that would take us to heads. I would go from losing to winning. And so consequently, tails, heads is not a pure strategy Nash equilibrium. You notice anything? We got no equilibria. Heads, no. Heads, tails, no. Tails, heads, no. Tails, no. We don't have a single pure strategy Nash equilibrium. So the funding agency called, and they're like, neat job writing down Matching Pennies. And we're like, thank you. We worked pretty hard on it. And then they'd be like, and what is your prediction? What conclusions have you reached? Tell us, this is why we funded you. We didn't fund you because we thought that it was really fun to think about obverse and reverse. We funded you because we want to know what the prediction is. And right now we're like, I got nothing for you, right? That's no good. So we have no prediction. There is no equilibrium given the tools that we've developed up to this point. Does that mean that this is hopeless? Does that mean that we're done? No, it does not mean that we're done. It does mean that we have to enrich what we mean by a strategy though. Go back to the end of lecture 4. Go back to the end of the expected utility lecture and you'll see a quick discussion of baseball, right? So right now you can think about row player like a hitter and column player like a pitcher, where the hitter is trying to figure out which pitch to sit on, and the pitcher is trying to figure out which pitch to throw. And there I described the origins of strategic randomness, the idea that strategic uncertainty arises because the pitcher would like to keep the hitter from guessing. And the way that they do so is by employing probabilistic strategies. Instead of always having heads up, instead of always having tails up, instead of always doing the same thing so that somebody would know what you were doing and therefore could condition their choices on what you were doing, which would be great in coordination, but which is awful in anti-coordination. Because of that, we need to think about randomization. We need to think about probabilities. And I want to do this by way of example. I don't want to make this too complicated. And so what I want to show you is the idea of a probabilistic strategy. I'm going to say that row player puts up heads. We're going to say that they put up heads with probability P, where they're choosing that probability. They don't choose heads or tails anymore. Now they choose the probability that they put heads up. It's almost like they program a computer to say heads with some probability, and then whatever the computer says, they go with it. Now they've sort of said, I'm leaving this up to fate, but on my own terms. I'm choosing the mixing probability. I'm going to choose the mixing probability, but conditional on that probability, the randomization is going to be what carries the day then. Okay? So suppose that it could be 1. If P is 1, then that's a pure strategy on heads. You're playing heads all the time. If P is 0, then that means you're playing tails all the time. But P could be 1/2, in which case you're playing heads with probability 1/2 and tails with probability 1/2. P could be 3/4, in which case you're playing heads with probability 3/4 and tails with probability 1/4. You're choosing a vector of probabilities to assign to each of your choices. That's really what a strategy is. How often would you choose each of your available choices? You might well be thinking to yourself, wait a second, why are probabilities being involved in a one-time interaction? And that's an excellent question. And most people, when they're playing rock, paper, scissors, don't have a computer open to do randomization. However, you'll see that this is a useful stand-in, this is a useful fable. You can think about the game being played many times. You can think about some degree of belief being placed on the available actions. Or for reasons that I'll show you in a few weeks, you might think of this as a stand-in for uncertainty about what kind of player I am, rather than what kind of action I'm going to choose. So just stay with me, put a pin in it if you need to. If it irritates you that we're doing a one-time thing probabilistically, it's very understandable. I have some replies, but let's just put a pin in those for now. So with probability P, I'm playing heads, and with probability 1 minus P, I'm playing tails. So I'm choosing a probability. I'm choosing a P. And then 1 minus P is how often I play tails. And that's my strategy. My strategy now, I've gone from choose an action to choose a set of probabilities over those actions, where I can still choose an action. If I play P equals 1, then that means I'm playing heads for sure. If I play P equals 0, that means I'm playing tails for sure. But now I'm allowed to choose from any probability between 0 and 1. Any number you can think of that lives between 0 and 1, that's an available probability. So I'm randomizing. And I'm just going to say the same for you. I'm going to say that you play heads with probability Q and tails with probability 1 minus Q, right? So Q could be 1, in which case you play heads for sure. Q could be 0, in which case you play tails for sure. Q could be anywhere in between, 1/4, 3/4, 7/8, 1/8. Whatever your favorite fraction is, it's in there. That's an available Q. So now I've enriched the possibilities of my two Matching Pennies players in a way that's similar to something that you've experienced when you play rock, paper, scissors. I should explain that. There's a children's game called rock, paper, scissors. And so the idea is children will go 1, 2, 3, and then they'll put out one of 3 hand gestures. Don't worry, this is going to be fine. So they could put out rock, they could put out paper, or they could put out scissors. I remember having some stock images of that. So they could play rock, they could play paper, they could play scissors. It turns out that certain combinations mean that one player won. So if I have out rock and you have out scissors, then I win because this rock can beat those scissors to smush the scissors. If I have out scissors and you have out paper, then I win because look, I can cut. Look at this cutting. Just imagine some very vivid cartooning. And for reasons that nobody quite fully understands, if I have out paper and you have out rock, then I win because I can envelop the rock with the paper, which just really shows that rock who's boss. If we have the same hand gesture, then that means it's a tie. We got to do it again. And whenever children play rock, paper, scissors, or at the World Rock, Paper, Scissors Championships, nobody plays the same thing every time. If you knew I was going to put out rock every time, you would put out paper every time. You wouldn't play a mixed strategy. You'd put out paper every time because that would mean you won every time, right? We've all experienced this feeling if we played rock, paper, scissors or some other similar game. We've all employed probabilistic strategies. And so all that I've allowed for is instead of making one choice, now you can employ probabilistic strategies. Some of the time you play heads and some of the time you play tails. Our quest is to try to find mixing probabilities that create harmony in the expected utilities. We're trying to find equilibrium just like before, where nobody wants to deviate. But now we're thinking, choose a set of probabilities from which you would not want to deviate. Find the best set of probabilities conditional on the other player's set of probabilities. What is your strategic randomization best response to their strategic randomization? Right? How should I keep you guessing? And how should you keep me guessing? And how do those two hows go together? Do those two hows go together in a harmonious, equilibrium-y way? When we go to find mixed strategy Nash equilibria, this is the main trick. If you understand the following substantive point, then you're going to be fine. Put your pencil down for a second. Don't write this down like equations just yet. Just stay with me. I'm row player, you're column player. What's up? So, the only reason that I would be willing to mix, right now I'm mixing some probability P, which is neither 0 nor 1, because if it was 0, you would have a best response. And if it was 1, you would have a best response. Right? If I was playing a pure strategy, you would have a best response in pure strategies, and that best response in pure strategies would not yield an equilibrium. We've already determined that there's no pure strategy equilibria in this game. So the only reason I would be willing to mix by which I mean choose a probability strictly between 0 and 1, truly some of the time I play heads and some of the time I play tails. The only reason I would be willing to do that is if the two options yielded the same expected utility. Otherwise, I would just choose whichever one yielded the higher expected utility, and I would choose it all the time. I would play a pure strategy. The only reason I would be willing to mix is if I was indifferent over the things I was mixing over. That's the only reason I'd be willing to mix. Otherwise, I would play a pure strategy. I'd figure out which one yields the strictly higher expected utility, and I would choose it all the time. If I thought my expected utility from playing heads was 1.2 and from playing tails was 0.8, if I thought those were my two expected utilities, I'd just play heads all the time. The only reason I'd be willing to mix, which I need in order for the funding agency to be okay with me, the only reason I'd be willing to mix is if I was indifferent over these two options. So I need to think about role players' expected utility, and then I need to figure out how to equalize it. Otherwise, role player wouldn't be willing to engage in this thought experiment of strategic randomization. If you understand that, we're going to be fine. Because what I'm going to do is I'm going to get the expected utility of heads, the expected utility of tails, and then set them equal. And then you're going to be like, oh, so that's what he did. And that isn't just what I did. What I did was what I told you. What I did was I'm going to say, what's the expected utility of one? What's the expected utility of the other? The only reason I'd be willing to mix is if they were the same. Therefore, let me go find the mixing probability. And then in the C block, you'll see that there's actually a final extra step to make sure that we're good. In a 2x2 game like this, it's pretty straightforward. It's almost a little bit too straightforward. Just stay with me. Just have open eyes and have open ears for the rest of the lecture, as opposed to the other lectures. You're just gonna have to trust me a little bit here. So I need to think about role players' expected utility of heads and of tails. Otherwise, if they weren't the same, they wouldn't be willing to mix. So what is the expected utility of heads? Well, if I play heads all the time, if I played heads every time, if I played heads every time, then with probability Q, you played heads, we're at heads, and I get 1 happiness point. So my expected utility begins with a Q times a 1. And with probability 1 minus Q, you played tails. Well, that means I get -1 happiness points, right? So that's 1 minus Q times -1. And that's my whole expected utility. With probability Q, we're at heads. With probability 1 minus Q, we're at tails. That gives me 1 and -1 happiness points respectively. Therefore, my expected utility is Q times 1 plus 1 minus Q times -1, which is 2Q minus 1. 2Q minus 1. My expected utility of playing heads is 2Q minus 1, depending on your Q. If your Q was 1, so that you're playing heads all the time, I'd get 2Q minus 1, that's 1, which is what I get for heads. And if you were playing tails all the time, so that your Q was 0, then I would get 2Q minus 1 is -1, which is what you get, which is what I get for heads tails. And the idea is that I can get any expected utility in between by varying the Q. So whatever Q is, it's going to create an expected utility that lives somewhere between -1 and 1 for me on heads. So my expected utility, if I played heads all the time, then I would expect to get 2Q minus 1 happiness points. I'm thinking about what all the hypothetical Qs you could be playing. Well, let's think about tails. So with probability P, we're at tails heads and I get -1 happiness points. And with probability 1 minus Q, we're at tails and I get 1 happiness point. So my expected utility of playing tails is Q times -1 plus 1 minus Q times 1, which is 1 minus 2Q. 1 minus 2Q. So let's think about what my best response is. What would be my best P in response to any Q that you could play? Let's think about my best response, not what we just learned, given what we just learned, okay? So the expected utility for me playing heads is 2Q minus 1, and the expected utility for me playing tails is 1 minus 2Q. So let's think about this for a second. So suppose that Q was strictly greater than 1/2. If Q was strictly greater than 1/2, if you were playing heads pretty often, then 2Q minus 1 would be strictly greater than 1 minus 2Q. Q equals 1/2, that's like the cut point. So if Q is strictly greater than 1/2, I'm best served by playing heads all the time. And so my best response to any Q that is strictly greater than 1/2, my best response to any big Q is to play heads all the time, which is to say set P equals to 1. So my best response, the best P that I could choose, it's a pure strategy. The best response I could choose for if you play heads sufficiently often, the best thing I can do is to choose the pure strategy heads all the time. the degenerate lottery of heads all the time, the pure strategy of heads all the time, which I'm calling 1 because we're allowing for randomization. But when I set p equals to 1, that means heads all the time. Similarly, if q is strictly less than 1/2, then 1 minus 2q, the expected utility of tails, would be strictly more than 2q minus 1, the expected utility of heads. So if you're playing tails sufficiently often, then I'm going to set p equals 0. I want to play tails all the time too, because the 1 minus 2q expected utility I get for that is strictly more than the 2q minus 1 expected utility I get for heads. However, if q is exactly equal to 1/2, if q equals 1/2, then these expected utilities are the same exact thing. 2q minus 1 equals 1 minus 2q equals 0. And consequently, I could choose any probability and get the same exact utility. If I'm getting 0 here and 0 here, then if I play this 0 70% of the time and this 0 30% of the time, that's still 0. And if I play this 0 20% of the time and this 0 80% of the time, that's still 0. Importantly, with the pure strategies as well, if I'm always up here, that's 0. If I'm always down here, that's 0. So in other words, it doesn't matter which p I choose if you happen to choose q equals 1/2. That's when I'm willing to mix. That's what I'm willing to mix. Otherwise, I'm not willing to mix. Let's do the same for you. So your expected utility for heads, right? Your expected utility for heads with probability p, where it heads and you get -1 happiness points, and with probability 1 minus p, where it tails heads and you get 1 happiness point. So that's p times -1 plus 1 minus p times 1, that's 1 minus 2p. 1 minus 2p. Your expected utility of heads is 1 minus 2p. Your expected utility of tails is with probability p, we're at heads, tails, and you get 1 happiness point. And with probability 1 minus p, we're at tails, and you get -1 happiness points. So that's 2p minus 1. So these are the same looking things. 1/2 is again the cut point, but this time, because it's anti-coordination, now it's if p is sufficiently high, you want to play tails all the time. If you think I'm going heads a lot of the time, you're going to set q equals to 0. You're going to avoid me by playing tails all the time. You're the avoider, I'm the looker, seeker. There's an opportunity for some Harry Potter references and I missed them. Similarly, if p is less than 1/2, if I'm playing tails sufficiently often, if p is less than 1/2 and I'm playing tails sufficiently often, then you want to avoid me by playing heads all the time. And so you'll avoid me by setting q equals to 1. However, at the situation where I'm playing heads with probability 1/2, again, you're indifferent, you don't care. So you could choose any mixing probability, you could choose any q between 0 and 1. And it wouldn't matter, you would get 0 happiness points no matter what mix you chose. So we have now officially encoded best response when you're allowed to mix it up. When you're allowed to mix it up, here's how you get best response when you can mix it up. We've allowed for strategic randomization. Now what I want to do from here is I want to plot the best responses. I want to plot the best response correspondences. I want to plot these things that we just derived. Because I think that that'll help you to see what equilibrium looks like. So I'm going to make a square. And in this square, I'm going to plot the probability that I play heads, p, on this axis. So here p equals 0, here's p equals 1. I'm going to plot the probability that you play heads, that's q, on this axis. So here's q equals 0, here's q equals 1. So I have a square. There's 0, 0, there's 1, 0, there's 0, 1, there's 1, 1. All right? So in fact, all 4 of these corners are pure strategy profiles. Right? So here's tails, tails. Here's heads, heads. Here's heads, tails. Here's tails, heads. So the pure strategy profiles are just the corners of this square. But I'm also allowed to use the entire juicy interior of this particular mathematical cookie. I didn't see that one coming. So I plotted the pure strategies, but I'm allowing for mixed strategies as well. So let's plot my best responses here. Right? So let's choose which p's are the best response p's conditional on any q. So you'll remember that the cut point was q equals 1/2. So let me put in a q equals 1/2 cut point. All right? So this is q equals 1/2. Here's q equals 0. Here's q equals 1. And here's the idea. So if q is strictly less than 1/2, if we're south of the border, if q is strictly less than 1/2, then I want to choose a low p because that means that you're not going to heads, you're not playing heads enough. If Q is less than 1/2, you're playing tails pretty often. I want to play tails pretty often. So I'm going to set P equals to 0. I'm going to do that by just tracing the axis. So here's that. And when Q is strictly greater than 1/2, if we're north of the border, then I want to jump all the way over to playing heads all the time. Right? If you're playing heads pretty often, more than 1/2 of the time, then I want to play heads all the time. So I'm going to trace that. I'm going to say, I don't care. I just want to set P equals to 1. I'm just tracing the axis. I'm just tracing. So right now I've just got these two edges of the square highlighted. That leaves open the possibility that Q equals 1/2. And what we said was that Q equals 1/2. I don't care. I could choose any P. I could choose any P. So this shape is my best response correspondence. This shape is my best response correspondence. If Q is low, I want P low. If Q is high, I want P high. And if Q is middling, I don't care. Let's do the same for you. So in order to do so, you'll remember that P equals 1/2 was the cut point for your best response. So whoosh. For some reason, I think that this ought to be a wong and this ought to be a shuk. I don't know why. It makes sense to me though. That you have a different kind of best response. Okay? So suppose that P is high. If P is high, if we're pretty far over to the right, if P is high, then you want to avoid me by setting Q low. If P is high, you want to set Q low. You want to set Q equals to 0. So if P is high, you trace the bottom of the square. And if P is low, if we're over here, then you want to avoid me by setting Q high. So you jump up. You go from playing tails all the time to playing heads all the time. And so I could just trace the top of the square. And again, if P equals 1/2, you're indifferent between your alternatives. You could choose any mixing probability and not care. Whoosh. Any place that these two correspondences intersect is a mutual best response. That means that I'm best responding to you, best responding to me. So if we see any intersections in the square, if the best response correspondences cross, then that's an equilibrium. Notice that there are no pure strategy Nash equilibria because there are no intersections at the corners. At this corner, I'm here but you're not. At this corner, you're here but I'm not. At this corner, I'm here but you're not. And at this corner, you're here but I'm not. There's never a corner where we're both there. Now, there is a point in the square, however, where they both are. If P equals 1/2 and Q equals 1/2, then P is best responding to Q is best responding to P, and so we have an equilibrium right in the middle. So heads half the time, tails half the time for me, heads half the time, tails half the time for you, is a Nash equilibrium in mixed strategies or just a Nash equilibrium. This is what an equilibrium looks like. This is what optimal strategic randomization looks like. Now that we've handled this, I can tell you something really important. Important by game theory standards anyway. Consider any game that has a finite set of players where every player is equipped with a finite set of alternatives. So let n, the number of players, be a finite number. And for every player I, let a sub I be a finite set, some set that you could write in roster notation if you wanted to. Any game that satisfies that finiteness property, finite number of players, could be huge but finite. And every player has a finite number of actions, could be huge but finite. Every one of those has at least one Nash equilibrium in pure or mixed strategies. And because pure strategies are just a special kind of mixed strategy, we could just say every finite game has a Nash equilibrium. That's called Nash's theorem. That's the reason that we call these Nash equilibria, was him proving that. Which is actually a really short proof. How short? John Nash's dissertation included this and Nash bargaining, and the whole dissertation was 26 pages. So pretty short proof. You've probably written a 26-page paper in your life, or if you haven't, you've probably come close enough that just think about how much work that took. Professors, they could write 26 pages and call it a grocery list. But a 26-page dissertation, maybe it's 28. It's either 26 or 28. It's an even number in the high 20s. That's how long the dissertation is. So it's a short proof. But what this means is if we write down a game with a finite number of players, each equipped with a finite number of alternatives, we'll never show up to the funding agency empty-handed. We always have at least one prediction. We might have multiple equilibria, but we'll always have at least one. We'll never have 0 predictions. Here, what we're saying is, half of the time, I'll put heads up, half the time, I'll put tails up, and the same for you. That kind of sounds like how people would play a randomized game like this, or rock, paper, scissors. If you were known as playing rock pretty often, but not all the time, people would still play paper against you all the time. If you played rock too often, people would play paper against you all the time. You'd have to adjust your probabilities. And so what a Nash equilibrium is a situation where you wouldn't tweak your probabilities anymore. You've optimized your probabilities. So that's pretty cool. So you have now seen the official, everybody's first introduction to mixed strategy Nash equilibrium. Matching pennies is where we all start with this. But I'm really looking forward to showing you in the remainder of the lecture some of the fun lessons you can learn from this. And so over in the B block, we're just going to do this entire exercise again on the game of chicken. I'll see you there. So here in the B block, I want to do the entire exercise again on the game of chicken. I don't know if you know this, but there's a really great song by Charles Mingus called Chicken. Charles Mingus is my favorite musician, and it goes like this. No, I'm just teasing. I wouldn't subject you to that twice. I almost cut the whole thing out of the last movie. I wouldn't do that to you twice. I'm already bashful. For what it's worth, I never quite know how much of the hijinks to throw in versus how much of just the content. I know that some of you just want to do your problem sets. I also know that this is a marathon that we're running. If you don't keep yourself entertained, then you're gonna go batty. And that goes for me too. So here's chicken. Remember, chicken is based on brinkmanship, rebel without a cause. I'm driving in a car towards you, or I'm putting a nuclear weapon really close to you. All right, game of chicken. So you'll remember that the idea here is that I'm in a car and you're in a car. We're in two cars. And I could either swerve or go straight as we're driving toward one another at very high speed. I can swerve or go straight. And you can swerve or go straight. If we both swerve, then that's a tie, and it's one happiness point apiece. If I go straight and you swerve, then I win, you lose, I'm awesome, you're a chicken, 2 happiness points for me, 0 happiness points for you. Same works in reverse. If I swerve and you go straight, I'm a chicken, you're awesome, 0, 2. And finally, if we're both very brave and we drive straight and neither of us swerves, then fiery car crash, -1, -1. You'll remember that this game has 2 pure strategy Nash equilibria, and they are the ones that involve winners and losers. So if I just put the stars into the game, you'll notice that there's 2 stars at straight swerve and 2 stars at swerve straight. So those are our 2 pure strategy Nash equilibria. You might be thinking to yourself, oh, well, we're going to be able to show up to the funding agency with predictions. Why are we going any further? And, well, one is it's good to characterize all of the possibilities of a game. If we thought that this was actually happening in the wild, there's no way for us to know which equilibrium would be the equilibrium to expect to see. Therefore, you need an exhaustive list of equilibria. Otherwise, you don't know if what you've gotten is going to be what happens in the real world. 2, it's good to be exhaustive whenever you can. And 3, it turns out that what I'll be able to show you with further analysis is quite interesting. So actually, before I begin the analysis, let me tell you something interesting. And it's a good way to know when to quit. It's somewhat esoteric, and so just forgive me for saying something esoteric. I'm going to say something that you can basically take as true, but it's actually only almost always true. It is almost always the case with probability 1. Almost all games, right? Almost all games have an odd number of equilibria in total in pure and mixed strategies. And so right now I've showed you a game and I found 2 equilibria. That's an even number. I'm thinking to myself as an analyst, there's probably another equilibrium that I gotta go find, and it's gonna be involving some mixing because I found all of the pure strategy Nash equilibria. I will not write down a game for you to solve that has an even number of equilibria. I won't make you do that. So if you ever get to a situation where there's an even number of pure strategy equilibria, keep digging. If I've told you to find all the equilibria. I don't want you to be going in infinite circles or doing wild goose chases. So I want you to have a sense about when to stop. So here's a game with 2 pure strategy Nash equilibria, and therefore I'm looking for more. I'm going further. I'm going to keep digging. I'm going to look for a mixing equilibrium. So the first thing I want to do is make sure that there aren't any situations where one player plays a pure strategy and the other one mixes. So if I knew that you were swerving for sure, I wouldn't mix. If I knew that you were swerving for sure, I wouldn't mix. I would go straight for sure. I wouldn't mix. And I have a unique best response. I have a unique best, there's nothing indifferent here. I'd have to be indifferent over my options to be willing to mix. I'm not willing to mix if I know that you're swerving for sure. And I'm not willing to mix if I know you're going straight for sure, because then I'm going to swerve for sure. All right. So if you're playing a pure strategy, I'm playing a pure strategy. And the same goes in reverse. So you can confirm for yourself. And actually, I would suggest that you actually do that. Confirm for yourself, pause the video if you need to, and confirm for yourself that if I'm playing a pure strategy, so too will you. If I'm swerving for sure, you'll go straight for sure. And if I'm going straight for sure, you'll swerve for sure. Consequently, we're on firm footing just saying I swerve with probability P and you swerve with probability Q, and those have to be strictly between 0 and 1. That we're not going to consider any pure strategy possibilities. We're taking all the for sures out of it. This is going to be a totally mixed equilibrium. I'm mixing, you're mixing. Just like in Matching Pennies. It's just that here there were some pure strategy intersections. I'm going to swerve with probability P and not swerve, go straight with probability 1 minus P. And you're going to swerve with probability Q and go straight with probability 1 minus Q. Chewy! Quiet! Chewy says hi. So let's work out these expected utilities. Remember, I would only be willing to mix if I was indifferent between going straight and swerving. And you would only be willing to mix if you were indifferent between going straight and swerving. My expected utility for swerving. Well, with probability Q, you swerve. And we're at swerve and I get 1 happiness point. So that's Q times 1. And with probability 1 minus Q, you go straight, I've swerved, I'm the chicken, I get 1 minus Q times 0, which is just 0. So my expected utility for swerving is Q. Q times 1 is Q. Notice that if Q was 1, so that you were swerving all the time, my expected utility would be 1, which is what I get here. And if you were swerving none of the time, so that your Q was 0, then my expected utility would be 0. And I would get the 0 that I get for swerve straight. What is my expected utility for going straight? Well, with probability Q, you swerve, and that means I get 2 full happiness points. So that's 2 times Q plus 1 minus Q times the minus 1 that I get for the fiery car crash. So that works out to 3Q minus 1. 3Q minus 1. So I'm comparing Q against 3Q minus 1. Now remember, I'm only willing to mix. I'm only willing to do the analyst the favor of mixing. I'm only willing to swerve some of the time and go straight some of the time. I'm only willing to mix if I'm indifferent between swerve and straight. Otherwise, I would choose one for sure, right? I choose a pure strategy. And so if you work out when does Q equals 3Q minus 1, that's when Q equals 1/4. Wait, what? So I would only be willing to mix if you were swerving 1/4 of the time and going straight 3/4 of the time. No. That isn't right. No. Hey, everybody. Welcome to the errata for Lecture 9 of PS 398. We haven't met yet. I am Editor Rob. I am the person that has been behind the scenes making these movies look so awesome all the time. You're welcome. The babyface, he gets all the credit, he gets all the accolades. Oh, hey everybody, welcome to week whatever of PS 398. But what's he do? He screws his algebra up. So now here I am, I gotta do all this work on his behalf. And you know what? I don't get treated all fancy like the babyface does. You know, Editor Rob, despite being the unseen genius behind PS 398, doesn't get anything. You know what I'm drinking? I'm drinking coffee like a regular person. Oolong tea. Oh, I'm drinking oolong tea, or I've got rooibos tea. Go to hell. So what happened is the babyface did make an actual little mistake, and it was going to throw off a couple minutes of the lecture. And instead of leaving things in his incredibly incapable hands, I just figured it would be easier to talk to you now directly. This is not my strong suit. I don't really know how to do this. That guy, he's developed a lot of skills in that regard, although he still can't aim his rows and his columns, right? And so I just want to get us to where we need to go, and then I'll let him go back to being the ham that he is. But never let it be said that there's one person behind all of this, you know? So the gaffe that the babyface made is that he said that if 3Q minus 1 equals Q, then Q equals 1/4. That ain't even remotely close to true. So you'll notice that when Q equals 1/2, I, role player, am indifferent between swerving and going straight. Why? Because my expected utility of swerving is Q, that's 1/2, and my expected utility of going straight is 3Q minus 1, which is 3 times 1/2, that's 3 halves, minus 1, that's 1/2. You'll note that that's when things are equal. Nevertheless, your PhD holding professor conducted the entire analysis twice on the back of an envelope and got it wrong twice. Don't believe me? Let's go to the footage. Oh, here he is. He's provocatively rubbing his beard. He's thinking to himself, how wrong could I be as I did this calculation? Is that true? Oh, is it true? Oh, here he goes to the back of an envelope, to the back of a wastewater system, to the back of a sewage envelope. Oh, he's working. He's working. Q times 1. Here's a chance. Q? Here's a chance. Here's a chance. 2Q. Plus Q minus 3. No, the math doesn't check out! The math doesn't check out! The most annoying thing about all this isn't that Babyface gets all the credit. The most annoying thing is that I can hear our dad in my head saying, now who's bad at math, son?
Now who's bad at math, son?
See what I mean? It gets even worse if you imagine it in front of elk antlers.
Now who's bad at math, son?
See what I mean? It's worst of all in front of awesome paintings of Pittsburgh.
Now who's bad at math, son?
See what I mean? So now my dreams are going to be haunted by that, all because Babyface was too busy to get out a clean piece of paper to do his chicken analysis. Somehow that's the sentence that I intended to say. You know, I should cut Babyface some slack. He's been working pretty hard too. You know, those sessions get pretty grueling, especially the day after he got a vaccine. And it's important that you're good to yourself too. You know, we all make little stupid mistakes. And that doesn't make us stupid, that just means that the mistakes are stupid. Careless accidents happen all the time. And that happens especially in the case of literal back-of-the-envelope calculations like the Babyface was trying to pull off yesterday. You know, give yourself the time and the space to do things right. Babyface tries to keep paper away so that there aren't too many white specks in his eyes, and the result is he screws things up now and again. For which he's sorry, I'm sure. Thankfully, there's one and only one thing that Babyface and I agree on. And that's that there's no such thing as mistakes, only happy accidents. So I've got about 10-15 minutes of lecture to give you, so let's get started. When are you indifferent? We need to work out your expected utilities. Well, it turns out that your expected utility of swerving, with probability P, I've swerved as well, and now we find ourselves at the swerve, and you get 1 happiness point. So that's P times 1. Plus 1 minus P. 1 minus P, with probability 1 minus P, I've gone straight and you're the loser, which means you get 0 happiness points. Therefore, your expected utility of swerving is just P. Similarly, your expected utility of going straight is, well, with probability P, I'm swerving. That means that you win, so it's 2 times P, 2 happiness points for the win times the P, plus 1 minus P, with probability 1 minus P, I'm going straight. That means we're in a fiery car crash, which means that you get minus 1 happiness points. You work all that out, you get to 3p minus 1. An interesting question, therefore, is when is 3p minus 1 equal to p? And just as before, that's when p equals 1/2. So let's think about best responses. We can intuit our way through the best response correspondence relatively easily. Let's think about row player first. Let's think about player 1. So if Q is low, so if you're not swerving very often, if Q is strictly less than 1/2, if Q is strictly less than 1/2, then that means that I don't want to go straight because I don't think you're swerving very often. So if Q is strictly less than 1/2, I would rather swerve. And so I'll set P equals to 1. So if Q is low, if Q is strictly less than 1/2, my best response is the pure strategy of swerving. Similarly, if Q is strictly greater than 1/2, so if you're swerving pretty often, then I want to go straight pretty often. So if Q is strictly greater than 1/2, then I want to go straight all the time, and I'll set P equal to 0. And if P is exactly equal to 1/2, I'm indifferent between these two alternatives. I don't care if I swerve, I don't care if I go straight, I don't care if I mix over them with any kind of probability, therefore any mix will suffice, and so P could be any P between 0 and 1. So my best response is just like before, it's just if you're swerving often, I go straight all the time. If you're going straight often, I swerve all the time, and if you're at just the right balance, if Q equals 1/2, then I could do anything. The same goes for you. So if P is relatively high, if I'm swerving pretty often, you'll go straight all the time. You'll set Q equals 0. If P is relatively low, if I'm not swerving very often, you'll swerve all the time. You'll set Q equals to 1. And if P is exactly equal to 1/2, then just like before, you can choose any Q and it doesn't matter because you're indifferent between these two alternatives. Otherwise, you wouldn't be willing to mix is what we're going to try to exploit here. So we can make that same square again. We can make that best response correspondence square. Boom, boom, boom. Okay? Where the idea here is that here is p equals 0. This means I'm never swerving, always going straight. And here's p equals 1. This means I'm never straighting, I'm always going swerve. And the same with q. Down here, q equals 0. That means that you're never swerving, you're always going straight. And up here is q equals 1. That means you're never straighting, you're always going swerve. I'm just as eloquent as the baby face. That's not saying much, is it? Let's put row player's best response correspondence first. You'll remember that the cut point q is at q equals 1/2, so let's put that q there. So, if q is strictly less than 1/2, if you're not swerving very often, if you're going straight too much of the time, then that means I'm always going to want to swerve, and so I'll set p high. I'll set p all the way equal to 1. Similarly, if q is high, if you're swerving pretty often, if you're swerving a lot, then I'll go straight all the time and I'll set p low. And at q equals exactly 1/2, I'm indifferent and any p would do. So I go whoop, whoop, whoop along 1/2, not 1/4, babyface. What about you? You're column player. So again, the relevant p cut point is at p equals 1/2, so I'll put a shoom there. Well, if p is high, if I'm swerving a lot, then you're going to want to go straight. You're never going to swerve, and so you'll choose down here. You'll just trace the bottom of the square. Similarly, if p is a low number, if I'm not swerving very often, then you want to swerve a lot, right? So you're going to set q high. And at p equals 1/2, you don't care. Any q will do. So I go up, over, up, and you go over, up, over. You'll notice that we have intersections of these two corners. What are these two corners? Well, over here we're at p equals 1, which means that I'm swerving for sure, and q equals 0, which means that you're going straight for sure. That's the first pure strategy Nash equilibrium, the one where you win and I lose. Similarly, up here, this means p equals 0, which means that I am going straight all the time, and q equals 1, which means that you're swerving all the time. This is the one where I win and you lose. You'll notice, however, that there's a third equilibrium right in the middle. That's at 1/2, 1/2. I go straight half the time and I swerve half the time. 1/2, 1/2. You go straight half the time and you swerve half the time. That's a mixed strategy Nash equilibrium in this game. We have 3 equilibria, the 2 pure strategy equilibria and this 1 mixed equilibrium. So that's pretty cool. We already had 2 equilibria, but it turns out there was a third one lurking there. We just had to look hard enough for it inside of the delicious inside of this cookie. Now what I want to do is I want to show you how we can compare what happens in the mixed equilibrium against what happens in these 2 pure equilibria. And I want to do so from a utility imputation standpoint. So I need to get a utility imputation space cooking. Here it is. I'm the one, I know I can say to you, I made this picture. Aren't you proud of me? I'm editor rub. Babyface, he doesn't know how to draw at all. He can't draw anything. You should see the things that he draws. Now check this out. So I'm going to put all 4 of the pure strategy imputations into this space. What does that mean? Well, I can go over 2 and up 0, and that's the situation where I won and you lost. This is the straight swerve. And up here is the swerve straight. That's the one where I have 0 happiness points and you have 2 happiness points. There's the one where we tie, which is at 1-1. And there's the one where we earn a fiery car crash. That's -1, -1. All right, so these are our 4 pure strategy utility imputations. So what I want to do is I want to work out the expected utilities the players experience if they play this mixed equilibrium of 1/2 against 1/2. So an interesting question then is, how often does each of the 4 outcomes in our square happen? How often do each of the 4 outcomes happen? Remember, I go straight half the time and swerve half the time, and you go straight half the time and swerve half the time. And those are independent of one another. Right? So I can just multiply the probabilities together and I wind up with the right probabilities. You'll see what I mean here in a second. For example, how often does swerve happen? Well, it happens 1/2 of the time times 1/2 of the time. That's 1/4 of the time. So with probability 1/4, we are at swerve. With probability 1/4, we're at swerve straight, where you win and I lose. With probability 1/4, we're at straight swerve, where I win and you lose. And rather tragically, 1/4 of the time, we're at -1, -1, which is associated with straight, a fiery car crash. 1/4 of the time, there's a fiery car crash. Quarter of the time, there's a fiery car crash. That sounds a little bit wasteful to begin with, don't you think? That sounds pretty bad. Let's see what happens. So let's think about this. So let's get my expected utility for this. Role player's expected utility, adolescent A. Well, with probability 1/4, I get 1 happiness point for swerve swerve. With probability 1/4, I get 0 happiness points for swerve straight. With probability 1/4, I get 2 happiness points for straight swerve. And with probability 1/4, I get -1 happiness points for straight straight. That works out to 1/2. That works out to 1/2. What about you? You're column player. Well, 1/4 of the time you get 1 happiness point for swerve swerve. 1/4 of the time you get 2 happiness points for swerve straight. 1/4 of the time you get 0 happiness points for straight swerve, and 1/4 of the time you get -1 happiness points for straight straight. So your expected utility for playing this equilibrium is also 1/2. So in expectation, if this is what was happening, if this was the equilibrium we landed on, my expected utility is 1/2 and your expected utility is 1/2. We've introduced a lot of strategic randomization into this. We've optimized our strategic randomization in best response to one another. And that has yielded expected utilities of 1/2, 1/2. You'll notice that's egalitarian. So let's go to the back to the utility imputation space and put this 1/2, 1/2 utility imputation in here. And I got a hard question for you. How do you compare waste and fairness? Why am I asking you that? Well, let me highlight the 2 pure strategy Nash equilibria, which are the ones where I win and you lose, and the one where you win and I lose. 2-0 and 0-2. You will notice that those lie along the Pareto frontier. They are Pareto efficient. No outcome. Pareto dominates the win-lose and the lose-win outcomes. The mixed equilibrium, however, is dominated. It's dominated by the one where we tie, the 1-1, or that could be micro-founded as half of the time you win and half of the time I win. Right? We could set up a system where we toss a coin, and if it's heads, we play the one where I win, and if it's tails, we play the one where you win. That would yield us expected utility of 1-1 as well, which also Pareto dominates the 1/2, 1/2 of our mixed equilibrium. So in other words, I've got a broken heart here. We've got a weeping chicken on our hands, and the reason we have a weeping chicken on our hands is that the 1/2, 1/2 expected utility imputation that we get for the mixed equilibrium is Pareto dominated both by swerve swerve and by some appropriate randomization over the 2 pure strategy equilibria. We could come up with a scheme that beats this easily. We have created waste. And what is the manifestation of that waste? What does the waste look like in this scenario? It looks like cars being driven into one another. It looks like nuclear war potentially. It's really bad. It's really wasteful. Yeah, it's a half a happiness point apiece, but it's so much more than that. Right? So in other words, in this stupid scribble called chicken, in this stupid scribble that we call chicken, if you look at it hard enough, if you squeeze it, and if you think about how you compare these 2 competing normative interests of waste and fairness, yeah, you can come up with a fair outcome, but in order to get there, you're going to have to put up with some car crashes. Getting to the egalitarian line in this scenario requires conflict, costly conflict, being willing to go to the mattresses, being willing to be in a car crash now and again. And even though it's Pareto dominated, at least you got your share. And it beats losing. Right? If you knew for sure that we were playing the equilibrium where I win and you lose, then you are totally within your rights to say, you know what, we're going to Mixtown, which apparently is a place. Right? The 0 happiness points that you get for losing, that's beaten. But that means 1/4 of the time you're going to wind up in a car crash. 1/4 of the time you're going to wind up losing, just like before. So you only do better than losing half of the time. 1/4 of the time you're in a tie and 1/4 of the time you win. Right? And what we're saying here is the path to trying to balance these utilities, that path is wasteful. Chicken highlights just how much conflict can play into the act of trying to get toward the egalitarian line, and it highlights just how much of a broken heart cost that might require. So when I ask you how you compare these things, I don't have an answer in mind. You can compare them however you want to. But one interesting question is, does your answer about comparing waste and fairness in domestic contexts, is it the same as your answer about waste and fairness in international contexts, now that you've thought about it from the perspective of this chicken equilibrium? You might have to ruminate on that. I hope that you will. This stupid scribble. This gives us an awful lot to think about, don't you think? So now that we've clarified this, that idiot babyface is allowed to come back on screen and finish up this B block that he so mercilessly screwed up with his math gaffe before. Back of the envelope doesn't mean literal back of the envelope, Rob. My apologies for the aside. It was very nice meeting you. We may never see one another again. Thanks for watching. So chicken just keeps getting better and better. One stupid scribble. If you look at it hard enough, if you just keep squeezing the same thing, you get more and more insight out of it. There's a lot to be said for that, I think. That's what's beautiful about having a book of fables, is there's one sort of standard set of stories, and then you can squeeze it as hard as you need to. There's always something more in there if you just keep poking at it. So now that we've revisited all of the delights of waste and fairness, it's time to talk a little bit more about actual world history, and so I'll show you something pretty cool about that over in the C block. So let's talk about June 1944. Somewhat monumental month in world history. So in June 1944, the Allied powers were planning an invasion of France, which was occupied by Nazi Germany during World War II. So when one is developing a strategy for such a campaign, it's difficult to know where to devote one's resources. And it turns out that before the D-Day attack, before Operation Overlord, there were 3 candidate beaches in France. 3 candidate beaches in France for where the Allies were considering landing their main force for this massive surprise attack. This massive campaign, which is going to start from a single bottleneck and then wash all over France, was the idea. And so the 3 ports that they considered, the 3 beaches that they considered, were Brittany, Calais, and Normandy. And so I'd like for us to play a little game called Wait, Which Beach? It's going to be a 2x3 game. Player 1 is going to be the Allied powers, and player 2 is going to be Germany. And so I'm going to write down the game, I'm going to tell you the story of the game, and then I'll analyze it a little bit, and then I'll leave some more for the problem set. And you're like, oh boy, thanks for leaving me something. So the basic idea is that the Allied powers, that's role player, the Allies, can either attack Calais, attack Normandy, or attack Brittany. There's 3 different beaches that they could set their sights on for where they were going to send their forces. Now, I'm not sure if you noticed, but defending armies are allowed to figure out where they're going to set up their defenses. That's kind of an important part of strategy as well. And so column player, that's player 2, that's Germany, they can either defend Calais, defend Normandy, or defend Brittany. The basic idea is much like with Matching Pennies. The Allies, the attacker, doesn't want to go where the defender is. You're best served to attack. If this is a surprise attack, you don't want there to be a defending army just waiting there for you saying, hey, what's up? You don't want that, right? So in the situations where we're on the diagonal, in the situations where it's Calais, Calais, Normandy, Normandy, or Brittany, Brittany, those are going to be situations where the Allies get 0 happiness points. They get 0 happiness points. They don't want to get caught somewhere. They're the avoider. So the situations that the Allies want to avoid, they want to avoid being on the main diagonal. They don't like the situations where we're both at Calais, we're both at Normandy, or we're both at Brittany. They're not big fans of that. I'm going to call the utility for Calais, Calais for the Allies. That's going to be 0 happiness points. I'm going to normalize the cost of attacking Calais to 0. You'll see what I mean in a second here. Then we'll say that the cost of attacking Normandy and getting caught there, we'll call that minus CN, where that's like, it's CN worse. Suppose that Calais is the easiest place to attack. Then minus C sub N, all that does is add an extra cost for being caught in Normandy. And then we'll have minus C sub B for Brittany, Brittany. That means getting caught at Brittany. And so we'll say Calais is the easiest place to attack, then Normandy. So CN is strictly greater than 0. And then CB is strictly greater than CN. So the Allies' favorite place to attack would be Calais. They prefer getting caught at Calais to getting caught at Normandy. And they prefer getting caught at Normandy to getting caught at Brittany. Just the beaches offer differential incentives. For example, Calais was the closest to British naval bases. So if the Allies attack Calais and don't get caught, if the Germans were defending Normandy or defending Brittany, then we'll say 1 happiness point for the Allies and 0 happiness points for Germany. At the situations where the Allies attack Normandy and don't get caught, we'll say 1 minus C sub N happiness points for the Allies and 0 points for Germany. And at the situations where the Allies attacked Brittany and didn't get caught, we'll say 1 minus CB happiness points for the caught. It's harder to attack Brittany, but if it worked, that's great. 1 minus CB for the Allies and 0 for Germany. And if the Germans catch the Allies, if they sent their defenses to the same place that the Allies sent their offense, then that's 1 happiness point for Germany. So 0, 1, minus CN1, minus CB1, that's all the ones where the defense was successful. 1, 0 for successfully attacking Calais. 1 minus CN0 for successfully attacking Normandy. And 1 minus CB0 for successfully attacking Brittany. First thing I'd like to do is confirm that this game has 0 pure strategy Nash equilibria. To do so, I'll just put in some best response stars really fast. So if the Allies knew that the Germans were going to be defending Calais, they would go to Normandy. 1 minus CN is higher than 1 minus CB and is higher than 0. Sorry, the costs are going to be less than 1, so it's 0 is less than CN is less than CB is less than 1. So the Allies' best response to defending Calais is to attack Normandy. The best response to defending Normandy is to attack Calais, and the best response to defending Brittany is to attack Calais. Calais is the easiest. You'd go there if they could, and if you can't, you'll go to Normandy. And the Germans' best response is very easy. They just want to stay on the diagonal. So if they knew that the Allies were attacking Calais, they would defend Calais. If they knew that the Allies were attacking Normandy, they would defend Normandy. And if they knew that the Allies were defending Brittany, they would defend Brittany. And you'll notice there's no cell that has 2 stars in it. So there are no pure strategy Nash equilibria. Notice that there's all sorts of different ways to mix. Right? So if I'm the Allies, it's true. I could play Calais for sure. I could play Normandy for sure. I could play Brittany for sure. I could mix with some probability P over the top 2. So I could go P, 1 minus P, and 0. I could mix over the top 3. I could go P, 0, and 1 minus P. I could mix over the bottom 2. I could go 0, P, and 1 minus P. Or I could mix over all 3. P sub C, P sub N, and 1 minus P, C minus Pn. So I've got a bunch of different ways to mix. And I'm only going to talk about one way here. And on the problem set, I'll talk about some of the other ways you might mix. I'm going to talk about the situation where the Allies mix over all 3. So we'll say that the Allies mix over all 3. Sometimes they go to Calais, sometimes they go to Normandy, and sometimes they go to Brittany. So there's a P sub C, a P sub N, and a 1 minus P sub C minus P sub N. Similarly, for Germany, I'm going to say that I'm going to consider the possibility that they mix over all 3. Right? So they defend Calais with probability Q sub C. They defend Normandy with probability Q sub N. And they defend Brittany with probability 1 minus Q sub C minus Q sub N. So this will be a situation where both players mix over all 3 beaches. The only way that the Allies would be willing to mix over all 3 beaches is if their expected utility from all 3 beaches was the same. So I need to work out the expected utility for the Allies of each beach. So the expected utility of attacking Calais. Well, with probability Q sub C, the Germans have defended Calais, and the Allies get 0 happiness points. So that's QC times 0. And with probability Q sub N, they've defended Normandy, and that yields 1 happiness point for the Allies. And with probability 1 minus Q sub C minus Q sub N, they've defended Brittany, and that yields 1 happiness point for the Allies. So in other words, the expected utility of attacking Calais is 1 minus Q sub C. Right, there's some QNs canceling out there. You get a QN times 1 and a QN times minus 1 here. So it's just 1 minus Q sub C. What's the expected utility of attacking Normandy? Well, with probability Q sub C, that's a successful attack, and so that's 1 minus C sub N. So QC times 1 minus C sub N. With probability QN, that's an unsuccessful attack, and you get minus C sub N. And with probability 1 minus Q sub C minus Q sub N, it's a successful attack, and you get 1 minus C sub N. You work all that out, and that works out to 1 minus Cn minus Qn. What about the expected utility of attacking Brittany? Well, with probability Q sub C, it's a successful attack, 1 minus C sub B. With probability Qn, it's a successful attack, 1 minus C sub B. And with probability 1 minus Q sub C minus Q sub N, it's an unsuccessful attack, minus C sub B. So you work all that out, and that works out to QC plus QN minus CB. I'm just working out expected utilities. This might look a little esoteric, but I'm just working out expected utilities. I'm just skipping over some tedious algebra. So I need to figure out which mixing probabilities, Q sub N and Q sub C, render the allies indifferent enough to mix over all three of their possibilities. Right? So I've got a system of equations now. Now I've got two conditions and two unknowns. So I need it to be true that the expected utility of attacking Calais is equal to the expected utility of attacking Normandy. So I need it to be true that 1 minus Q sub C equals 1 minus C sub N minus Q sub N. And I need it to be true that the expected utility of attacking Normandy is equal to the expected utility of attacking Brittany. There's a lot of words that go together here. And so that means that 1 minus C sub N minus Q sub N has got to be equal to Q sub C plus Q sub N minus C sub B. So you work all that out. You can solve systems of equations however you want to. So you work all that out, and it works out that the probability that the Germans defend Calais is 1 plus C sub N plus C sub B over 3. So in other words, as the cost of attacking Normandy goes up, and as the cost of attacking Brittany goes up, the Germans defend Calais more because they think it's less likely that they're going to see enemies at Normandy or Brittany. The probability that the Germans defend Normandy is 1 plus C sub N plus C sub B over 3 minus C sub N. So as the cost of attacking Normandy goes up, the probability of defending Normandy goes down. Finally, the probability that the Germans defend Brittany is 1 plus C sub N plus C sub B over 3 minus C sub B. Again, as the cost of attacking Brittany goes up, the Germans will defend Brittany less, and they will defend Normandy and Calais more. That's pretty cool, right? So as the differential cost, the German defenders are currently having to think through how often they're going to defend each place, and what they're conditioning on is how much better it is for the Allies to attack Calais versus Normandy and Normandy versus Brittany. They're taking those differential costs of attack into account in choosing where to defend. They're having to think about their enemy. They're having to think their opponent's costs through to determine what's the right way for them to mix. It isn't the Allies' cost that affect the Allies' probabilities. It's the Allies' cost that affects the German probabilities. Pretty cool, right? So that was the hard one. The Allies have it a lot easier in terms of finding their mixing probabilities. So we need it to be the case that the expected utility of defending Calais for the Germans is equal to the expected utility of defending Normandy, and we need that to be equal to the expected utility of defending Brittany. Well, thankfully, these expected utilities are very easy. So the expected utility of defending Calais is P sub C times 1 plus 0 plus 0. 0, 0. Easy. The expected utility of defending Normandy is P sub C times 0, 0, plus P sub N times 1, Pn, plus 1 minus P sub C minus P sub N times 0, that's 0. That's just P sub N. Finally, the expected utility of defending Brittany is P times C times 0, plus P times N times 0, plus 1 minus P sub C minus P sub N times 1, which is just 1 minus P sub C minus P sub N. So when does P sub C equals P sub N equals 1 minus P sub C equals P minus P sub N? That's when they're all 1/3. A third, a third, a third, a third, a third, a third, 1/3, 1/3, 1/3. So the Germans would only be willing to mix as we've asked them to in this equilibrium if the Allies were mixing 1/3, 1/3, 1/3. And the Allies would only be willing to mix as we need them to in this candidate equilibrium if the Germans were mixing in a way that respected the costs of different beaches to attack. This is a mixed strategy Nash equilibrium of this game, where the strategic randomization of where to go, where to attack, and where to defend is really interesting, because the Germans are explicitly taking into account the fact that the Allies are thinking about which places are the best places to attack. And the Allies are just trying to make sure that they can keep the Germans guessing as they defend. And in fact, this was actually a big part of Operation Overlord. In the immediate run-up to the June 6th invasion, in the immediate run-up, the Allied powers ran an intelligence campaign where they leaked information. They leaked fake information that said that they were going to attack Calais. And they leaked more fake information that said they were going to attack Brittany, when all along they were intending to attack Normandy. And the German intelligence forces that found this information therefore relayed the information back to strategy and said, hey, you need to defend Calais. You need to defend Brittany. And to the point that when the German intelligence officers found out that the attack was happening in Normandy, they thought that that was the fake, even though the attack had actually started. So busy were they defending Calais that they didn't get the attack in Normandy. So there was an explicit attempt to keep the opponent guessing. The strategic randomization went far deeper than just, oh, here's a system of equations. The strategic randomization involved faking the opponent out by sending them mixed signals. We're going to get to that momentarily, and by that I mean like 4 weeks. But even here, strategic randomization is really important on the battlefield. And one way to keep the enemy guessing in these anti-coordination games where offense and defense have competing incentives is to make sure that the opponent knows that you're mixing and to keep them confused about what kind of mix to expect. That's the power of strategic randomization. The ability to say, you think I'm going to Calais, but here I am at Normandy. So what do we talk about today? Well, we talked about extending the logic of Nash equilibrium to allow for strategic randomization. We took the promises of von Neumann and Morgenstern week. We took the promises of you got to keep the enemy guessing. You got to keep the opponent guessing. You got to make sure the batter doesn't know what kind of pitch is coming. And we really squeezed that as hard as we could. And we found out that that is actually the appropriate amount of squeezing to find out that we can always make a prediction. We have to squeeze at least a strategic randomization to get the mixed strategy Nash equilibrium to guarantee that a Nash equilibrium exists. Otherwise, games like Matching Pennies or Wait Which Beach or other games like Rock, Paper, Scissors, there is no prediction to make. And that's bad in its own right, but it also seems like we're missing an opportunity to take into account the fact that when a little kid plays Rock, Paper, Scissors, they really are mixing it up in their head. They're thinking to themselves, which one am I going to throw? And I know I can't throw the same thing every time. I can't let the opponent know what I am doing for sure. That strategic randomization is a really big deal at the scale of little kids making their decisions and of armies to figuring out which beach to attack. So when I said to you that there's always going to be some randomness in the world, that's because there's always going to be some amount of anti-coordination going on. Whenever you go to a wedding, you're going to meet some people that are pretty sure that you're friends, and you're not going to like them very much. And you're going to see them wedding after wedding after wedding. Every wedding you go to, you're going to see the same people, and there's this one person that thinks that you guys are really good friends, and you don't like that person at all. And so at the wedding, you're going to be involved in matching pennies, because they're going to be on the dance floor, and you will be in the bathroom. And then they will go to the bathroom, and you will be at the carving station. And then they will go to the carving station, and then you will go to the dance floor, and so on. There's always some randomization going on because you always want to avoid somebody, whether it's for reasons that are social, for reasons that are competitive, reasons that are military, reasons that are political. No matter what, strategy is strategy. However, we also had to give up some reality from the model in order to get to where we need to go to make a prediction. These games are played one time and one time only. There was only one June 6, 1944, thank God. Right? There was only one of those. You didn't actually attack Brittany a third of the time, Calais a third of the time, and Normandy a third of the time. You went to Normandy, right? The probabilities that one assigns for that, it's not like the Allied powers had some random number generator, and that said Normandy. They didn't actually assign probabilities. They didn't choose a lottery, all right? We had to give up some realism in order for this to make sense, and that might still be nagging at you, and that would be fine. And it's with this idea of being nagged by realism in mind that I'd like to conclude with a provocative thought. I know a lot of people that don't believe in mixed strategies. Oftentimes it's a problem. Let's say that you're a game theorist and you submit a paper to be refereed by a scholarly journal. There are some people, some referees out there, when they read the paper, other professors, when they read the paper, they'll be disappointed to see that equilibria only exist in mixed strategies in some parts. You could write down a game, and sometimes it has pure strategy equilibria and sometimes it doesn't. It only has mixed strategy equilibria. And oftentimes that irritates referees. It can irritate non-game theorists who think that doesn't seem very realistic. It can irritate military leaders who say to themselves, well, I'm not actually going to toss some dice and then figure out where to send my army. There are no iron dice that actually get rolled. You'd get thrown out of office if you said, well, time for randomization. This isn't guys' grocery games, okay? This is choosing where to go send people to fight and die. There is no randomization. So you might be thinking to yourself, that doesn't make any sense. And to a certain degree, it doesn't make any sense. There was only one June 6, 1944. There was only one D-Day. You only chose one beach. The fact that we couldn't make a prediction, the fact that we couldn't say, and they'll go to Normandy, the fact that we couldn't do that, does that mean that there's something wrong? Does that mean that the model is useless? Does that mean that games aren't very helpful? I mean, to a certain degree, yeah. If I'm being completely honest, it kind of stinks. I wish that we could write down a simple and straightforward model that said, and they go to Normandy. But the intelligence campaign that occurred prior to D-Day suggests that there was some degree of randomization going on, even if it was just at the informational, I'm going to fake you out kind of level. Even if the Allies knew they were going to Normandy, they knew that there was some benefit in making sure that the Germans had to guess about which beach to defend. And so we didn't write down something that said, oh, and the strategy is both which beach you're going to go to and which signals you're going to send out to the ethos. We didn't do that. Our model wasn't rich enough to capture that. But a good second best, a good consolation prize, is a model that involves some amount of mixing. Because that is somewhat of a stand-in. That's something of a stand-in for that idea of I'm going to keep you guessing. If I can't keep you guessing with my spies, I'll just keep you guessing with my fake probabilities. Something there is that still nags at you though. What is mixing? What is mixing? What is mixing? Is mixing keeping them guessing, or is mixing keeping yourself guessing? Is mixing making them thinking you're probabilistic, or is mixing being truly probabilistic? In order to be a true mixer, in order to be the sort of mixer that can survive in any Nash game, in order to be somebody that can be part of an equilibria in any game, be it chicken or matching pennies or wait which beach or whatever, in order to be the sort of player that can play in any game and arrive at some equilibrium, do you have to be a genuine mixer, capital G, capital M? Well, Nash's theorem suggests yes. You must, and there are games out there where the only people that land at equilibria are genuine mixers. But there's more to it than that. One of my favorite results in all of game theory is a little bit too complicated to show you. And it's one of those bummers. I'm not sure if you've noticed, but teaching this is hard. Teaching this is so hard. And I know I'm not doing the best job of it. And it's really tough. And I mean, I could do better, but it's also difficult for anybody. Even a more skilled teacher than I am would have trouble teaching you some of these things. So there's a more advanced thing that it's a little bit too hard to show you. But it is roughly the following. Suppose that you weren't allowed to mix. Suppose that you had to go to one beach or another beach. Suppose you had to play rock or had to play paper or had to play scissors in pure strategies. How could I micro-found something like randomization when I'm not allowing randomized strategies? If I'm not allowing strategic randomization, is there another opportunity to introduce some randomization into the game? And if so, could I write down a game in this alternate universe that only has pure strategies in it that gets the same outcomes as this mixed strategy equilibrium, which feels like a bit of a consolation prize? And the answer is yes. What would I randomize over? Well, suppose that there were three kinds of me. The kind of me that likes to go to Calais, the kind of me that likes to go to Normandy, and the kind of me that likes to go to Brittany. But suppose that you didn't quite know which kind of me I am. Suppose that the randomization wasn't about what I'm going to do, but about which me I am. Suppose that I had private information about myself, what type of me I am. Am I the kind that likes to go to Calais? Am I the kind that likes to go to Normandy? Am I the kind that likes to go to Brittany? And similarly for you, are you the kind that likes to defend Normandy? The kind that likes to defend Calais? The kind that likes to defend Brittany? There are different kinds of you potentially. We haven't talked about this yet. We'll be talking about this in a few weeks. I'm just asking you to entertain this thought for a second, where there's different kinds of me, but you don't know which. And there's different kinds of you, and I don't know which. There is now new uncertainty, not about what we're going to do, but rather about which opponent we're up against. And it turns out, and this is a really cool result, any mixed strategy equilibrium like the ones that we got today, any mixed strategy Nash equilibrium in a game where there is no uncertainty about the other player, but rather there is uncertainty about what they do, has a companion equilibrium in pure strategies where we don't quite know what kind of player we're up against. So in other words, I can take a complete information. I know which me I am. I know which you are. We both know what kind the other is, but we don't know what they're going to do. And we can take that and convert it into an equilibrium where we all know what the other will do for sure, but we don't quite know which type we're up against. Randomization can be about what I do or about which me I am. This is referred to as the purification of a mixed equilibrium. Any mixed equilibrium can be purified. Not purified in the sense that it is made pure, but purified in the sense that it is made pure. A pure strategy. This purification theorem is a reason for optimism and humility at the same time. I know it's hard to believe, but I'm going to talk about humility. I'm going to talk about it by contrasting it with optimism. On the one hand, it means that you think that there was a gotcha moment. You thought you gotcha'd me, and you thought that you gotcha'd Dwight Eisenhower. You thought that you gotcha'd by saying, well, there was only one D-Day. There was only one June 6th, and that's true. You are correct. But the model that I wrote down was just a first cut. It didn't include all of the interesting informational richness that gets involved in war. It didn't involve all of the different things that I know about myself and you don't know about me. And all the different things that you know about yourself that I don't know about you. All of the opportunities for private information have been stripped away. We haven't talked about that yet. There's only been one kind of every player. You know everything about me and I know everything about you. There's nothing to guess about in terms of who we're up against. We're only guessing about what they do. It seems quite plausible, however, that there is indeed private information on the battlefield. There are things that each fighter knows about themselves that their opponent does not know about. And so if you are willing to be patient, not humble, not charitable, but patient, then there exists some chance for a yeah but. And yeah buts are really interesting. So I say to you, this game has no pure strategy equilibria, but it does have an interesting one in mixed strategies. You say there was only one D-Day. I say, yeah, but this private information thing. And this, you say, yeah, but, you say, yeah, but, you say, yeah, but. That process is one of the most important processes in all of science. Your cynical but patient views on this, and my attempts to play ping pong with you, with yeah, but, yeah, but, yeah, but. There are problems with both approaches, both with the private information version and the full information version. The one where you're mixing over who I am and the one where you're mixing over what I do. There are problems with both of those approaches. But the fact that you can go from one and yeah but your way to the other means that you can try to avoid some of these pitfalls by being clever, by being a flexible, nimble analyst, which is what I would like for you to become by the end of this class. Somebody that's able to say, I see problems, I see potential solutions. The solutions are themselves problematic, I see solutions to those problems, and so on. There's an underlying pragmatism to our approach. The pragmatism is that there is no one capital T truth that we're chasing after. We're pursuing understanding in this iterative way. We're digging, because we won't know what the best model is ever. It's an iterative and evolutionary process. We come to understanding by comparing one argument against another and butting our way as we compare the two. That isn't to say that there aren't genuine gotcha moments. That isn't to say that there aren't genuine shortcomings of our approach. There are indeed genuine shortcomings. It's just that we have to go very far to bump into those frontiers. One of my very favorite quotes is that only those that go too far could possibly know how far one can go. The idea there is only those people that bump into the frontier and in fact go so far that they fall past the frontier, only they know where the frontier is. If you have not reached it, then you don't know where it is for sure. And so our understanding of things is this expanding bubble. And some thoughts expand out and raise, and some of them luckily go faster even than the bubble is expanding. They're truly great ideas. They move faster than the bubble expands. They are unique. They are singular. And whenever somebody gets to ride one of those beams of light faster than the bubble of understanding expands, then that person has some chance of knowing how far we can go. And whenever you get to that point where there is not yet a yeah but, when you're out of the heliosphere, when you're out in truly outer space, how beautiful must that be? When you can't hear the chaos of the yeah buts. When you can't hear the questions. When you can't hear the answers. When all that you see is what's outside the bubble. I've never been there. I sincerely hope that you get there one day. But you're only going to get there if you're nimble, if you're flexible, if you're creative, if you're charitable, and if you're humble. Thanks for watching.